Okay, super. So if you haven't had the pleasure to meet Steve Campbell, on my screen at least, he's on my right over here with the beautiful mountain behind him. Steve is a man of many responsibilities, but his title is Conservation Biologist. He designs studies to understand the effects of management on the preserve's plant and animal communities, manages the collected data, and he documents the results. And tonight he's going to talk to us about prairie warbler migration and geolocation. Take it away, Steve.
Okay, I'd like to start out by thanking those of you who are here, our volunteers. All that you do is really appreciated and contribute greatly to our success. I know with all this going on, volunteer opportunities at the preserve are limited, and I think it's great that you still want to remain engaged, and so I'm happy to help out by talking about some of the research that we have done. And specifically, I'll be talking about tracking prairie warbler migration with light-level geolocators. And this is research that, that we did in collaboration with Mike Akrash, who is now a professor at Antioch University in New Hampshire. Okay, well, before I get started, before I get into the specifics of the study, I want to just take a moment and provide just some context about migration, why animals do it, and why and how we study it. So I want to start very generally, just talk about the different types of animal movements. And I'm not talking here about flying or slithering or crawling, swimming or running. I'm talking about how they use the environment to meet their needs. So there are movements within their home range, as well as some exploratory forays beyond their home range boundaries. These movements are typically what we think of when we're talking about habitat use. Then there's a permanent departure from a home population or a natal area. This is considered dispersal. Usually it's a one-time event and is done primarily at the juvenile stage. And then there's these repeated movements between two or more home ranges. And these movements are typically seasonal, and these are migration, and these are the types of movements that we're concerned with in this study. So why do animals migrate? Well, one reason is to avoid the harsh climatic conditions, for example, heat and cold. And this can be accomplished through latitudinal movements. So for example, here's a sooty shearwater. These travel round trip between the Arctic and New Zealand to experience summers in both the northern and southern hemisphere. Animals can also avoid heat or cold by migrating altitudinally. For example, in the western US, you have mule deer that can migrate down out of the mountains each winter to avoid the cold, and then they will return to higher elevations in the following spring. And another reason to migrate is to follow the available food and water. Each year, wildebeest migrate between Kenya and Tanzania, and they are continually on the move in search of grass and water, and is all driven by rainfall, and their particular path and timing of the migration depends on the rainfall patterns of that particular year. And a third reason is because their life cycle requires different environments. For example, leatherbacks swim to the tropical beaches in Western Pacific to nest. They need the beaches to nest on. But then they go to the Eastern North Pacific, they go to the open ocean to forage. So they would need to migrate between those two locations. And sort of as an illustration of just how far animals will go to meet these, to meet their needs, consider these examples. An Arctic tern migrates from the Arctic to the Antarctic and back again every year. That's a 71,000 kilometer per year journey. That's by far the longest migration in the animal kingdom. So over its 30-year life cycle, or sorry, over its 30-year lifetime, that's about 2.4 million kilometers, or 3 round trips journeys to the moon. So that's not too bad for a bird that weighs about as much as a bar of soap. There's the humpback whale that feeds near the poles and gives birth in the tropics. So to get to both of these locations requires covering extraordinary distances, the longest of which is about almost 19,000 kilometers between, it's over here from American Samoa, between American Samoa and the Antarctic. That's another example. Another one that you might be familiar with is the monarch. This butterfly can migrate from as far north as southern Canada all the way to southwestern Mexico. And even more remarkable is the fact that it requires multiple generations of butterflies to make the round trip journey. Butterflies in the fall, they tend to live longer, about 8 months, and they'll make the migration down south in one generation. But on the way back up, it takes as many as 4 to 5 generations. They fly north, they stop, they lay eggs, and then they die, and then their offspring then hatch, grow, and pupate, and emerge as adults, then fly farther north, and the process repeats itself until they reach the northern limits. Okay, well, why do we study migration? Well, the ability to track individual migration route reveals wintering areas and migratory routes. This helps us to understand the ecology and habitat requirements of the species across its entire annual life cycle. It also reveals migratory time schedules. For example, what are the individual decisions to go in, when to leave an area, and when to initiate migration. More broadly though, detailed knowledge on the migratory strategies of a range of species is important for understanding the ecology and evolution of migration. For example, if you have comparative studies across species, that can help us to understand how migration evolved and how it can continue to evolve. And clearly knowing where they go and when can help with the conservation of migratory species. For example, knowing when to turn off city lights or shutting down windmills that are in the paths of migrating birds. And then finally, understanding migration will help us to understand how species and communities may respond to shifts in vegetation types due to climate change. Okay, so now let's talk about how we go about studying migration. One way is to uniquely mark individuals and then try to catch them at different points along their migration. Some examples of marking methods include uniquely numbered metal leg bands. In the case for birds, these are used. There can be neck collars. These have unique alphanumeric combinations that can be used on some species. Here you can see this is on a cackling goose in Alaska. These have an advantage over leg bands in that the animal does not have to be recaptured. You don't have to have it in hand to identify. The numbers can be read from a distance with either binoculars or a spotting scope. There are also passive integrated transponders tags, or these are called PIT tags. You may have heard of them. These are usually inserted subcutaneously and they act like barcodes in the grocery store. The PIT tags have no batteries. So there's a microchip remains inactive until is read with a scanner. The scanner sends a low frequency signal that actually to the microchip within the tag, and that provides the power needed to send the unique code back to the scanner and positively identify the animal. So for all practical purposes, it kind of works like a barcode scanner. And the PIT tag readers that you could use to detect the tags can be as simple as a handheld reader, or in the case you can see here, they have them hung over a stream. And so when the fish swim underneath these readers, it picks them up, again, like food going across the barcode reader at the checkout aisle. And in some cases, marks would just be as simple as stickers on the monarch butterflies. And this is not an exhaustive list here, but it gives you an idea of how different ways that you can mark individuals. So this all sounds good in theory, but in practice, this is not really a great way to study migration. First of all, you need to re-encounter the animal, either in hand if you're reading something small like this, or in line of sight if you're reading one of those neck collars. Secondly, is a really inefficient way to track animals. Just to give you an idea, we've banded thousands of birds at the pine bush over the last about 12 years. And out of those thousands, only 5 or 6 of our birds have ever been recaptured away from the preserve. So that's a lot of work to go into very little, that gives very little data on the migratory movements of animals. You can use radio telemetry to study migration. With this method, you attach transmitters to animals. The transmitters emit a radio signal that is picked up by a receiver with an antenna. And traditionally, radio telemetry was used to study local animal movements because the range of transmitters was really too limited to study migration. So if you put a transmitter on a migrating animal, it would quickly move out of range and they're going to be lost unless you're also migrating with the animal. However, the MODIS wildlife tracking system sort of changed all that. The MODIS wildlife tracking system is a collaborative research network that is comprised of automated radio telemetry arrays spread across the world that's all designed to study the movements of small animals. And the points on the maps that you see here, those show you where the MODIS stations in North America and also part of South America. We have one here at the top of the Discovery Center, which is what's pictured here in the lower right-hand corner. And the idea here is if you attach a transmitter to a migrating animal on its breeding grounds, as it migrates by one of these towers, the tower will detect the transmitter and then automatically record the observation. Now you might see the obvious limitations of this approach is that it's possible to put a transmitter on a bird and then have them miss all the towers along their migratory route as they fly south and not be detected either en route or on their wintering grounds. This problem is likely to increase over time as the network grows and starts to fill in the gaps. Here you can see we have a pretty good wall of these MODIS towers along sections of the eastern seaboard, so that it's very likely they're going to come in contact with one of these as they fly by. But the other limitation of this is the towers are expensive, as well as the supporting computer equipment that you need is also expensive. So that's also going to likely limit how many of these towers you can actually get set up in different locations. A very good way to study migration is by using GPS transmitters. Here you can see one attached to a tundra swan. And the GPS transmitters can be used to remotely obtain very precise locations and other data from animals anywhere in the world. These units record locations and then transmits that information to a satellite system. The data can then be accessed and downloaded to a computer and then mapped, as you can see here. So there's no need to follow the animals, which can be stressful for the animals. And if you're following them, if you're following animals with transmitters using helicopters or airplanes, it can actually be quite expensive as well as stressful. The limitations, so there's no need to follow these animals. So here's an example of you put these satellite transmitters on these tundra swans, and then you can just sit at your desk and the data come in showing you where they are on a given day. The limitations here, though, are that these units are very expensive. We're talking they're in the thousands of dollars. And currently they are too large for many animals. In order to have a battery strong enough to communicate with the satellites back and forth, requires a very large battery, which means the size of these things are just too big to be carried on many animals, especially animals that fly, like birds. GPS tags aim to solve the problem of the size and expense of GPS transmitters. These tags record locations of birds with the precision of larger GPS transmitters, and they store it on the GPS tags themselves. Because these are not transmitting the data back to the satellites, they need minimal battery power. And the batteries make up most of the weight of the transmitters. So these GPS tags can get really small as 1 gram, which really expands the range of animals that can be studied with this technology. Another benefit is that they're considerably less expensive than GPS transmitters. Each one of these is about $200. However, because they do not transmit data and the data are stored on the tag, that means the animal needs to be recaptured to get the data. That also means the smaller the tag, the lower number of points that you can record. And even the 1 gram tags are still too big for very small animals, especially if those animals that can fly. So you really couldn't put this on anything much smaller than, say, an eastern towhee. And that excludes many passerine birds such as the warblers. These even 1 gram transmitters are still too big for those species. We are using these GPS tags currently on whippoorwills in the preserve, and we're using these mostly to look at their local movement. So here you can see one bird here. This is the locations of one bird that was very likely mated with a female, which is probably why he was holding tight. And then here we had one on a second bird that you could see him moving all around. Likely he did not have a mate and was moving all around looking for one. So here, just to give you some perspective here, the preserve is over here. And you can see how far that bird moved all the way up to Vischer Ferry. Again, this is just home range use, but you can see the difference in the home ranges based on that. So we're using these just to look at local movements, but you can use these to look at the migratory movements of eastern whippoorwills, and some of our collaborators out at Worcester Polytechnic Institute are actually doing that work on whippoorwills. Okay, so finally that brings us to geolocators. So you can see now where the geolocators fit in with all of this. These geolocators are data logging devices that allow the inference of latitude and longitude from time-specific light intensity levels. So like satellite trackers, geolocators can obtain locations from animals anywhere in the world. Well, almost anywhere in the world. And you'll see what I mean by that. And it's important to note that like the GPS tags, these are just data loggers. They're only recording information. They are not transmitting any sort of signal. So these are just consist of a light sensor, a clock, and a memory device that are all integrated via a microprocessor. And so here you can see, here's one on the back of a thrush, and you can see here the light sensor is on the tip of the stalk. And that's to keep the light sensor elevated off the bird. And so these are really bare bone devices. That makes them small and light. They can be down to less than a half a gram. And it also makes them relatively inexpensive. Each one of these is about $100 a piece. However, because they are not transmitting data, again, you need to recapture the animal to recover the data. You need to recover those tags off the animals. And the geolocators are only recording light levels. So the location fixes, you don't just take the geolocator off and you have location data. What you have is light level data that then you have to post-process in order to get the location fixes. And as you'll see, latitudes cannot reliably obtained when there is when and where day length is 12 hours. And I'll come back to why that is. And then finally, you'll also see that these are less accurate than satellite tracking. Okay, so if I've done a reasonable job explaining the different ways of studying migration, hopefully you understand why we're using geolocators to examine the migration of prairie warblers. Your other question may be, and Dick asked me this earlier, is why are we studying prairie warblers? Well, for starter, prairie warblers are declining in North America, and the species is considered a species of greatest conservation need in New York. So to prevent the further decline of the species, we need to better understand its ecology over its full annual life cycle. Prairie warblers are tied very closely to the vegetation conditions of the pitch pine scrub oak barrens, which is a globally rare plant community. And we are putting a lot of effort into restoring and managing inland pitch pine scrub oak barrens. So we want to know if our efforts are working, if the populations of prairie warblers are responding positively to the management of the pitch pine scrub oak barrens. And if they are responding positively, then we know our efforts are being successful. And evidence that we are succeeding is that that prairie warblers are consistently abundant in the preserve. Their survival is relatively high. Here's survival estimates from a study that we did between 2009 and 2012. So we had about 70% survival from year to year, which is pretty good. And we also know that they are successfully breeding here in the preserve. But this is all well and good, but that is only what's happening during the breeding grounds. We can have great breeding habitat for them here, but if they can't make it to their wintering grounds and then back, it doesn't really matter so much what we do here. So we want to know how we're interested in how their activities in the non-breeding season, say from September to April, how are those tied in with the breeding season activities that we can see here at the preserve? And so some of the most basic yet important pieces of information we can learn about their time during the non-breeding season is where do they go and how do they get there? And we're also interested in prairie warblers from a methodological perspective. Geolocators are still a relatively new technology. They've only been in use for about 10 years. So the more bird species we look at, the better we can understand how well does this technology work and what are the effects of this technology on the birds. And prairie warblers are particularly interesting in this regard because they are one of the smallest birds so far to carry geolocators. They're only about 8 grams. So we were interested in the effects that geolocators may be having on this species as well as other similarly sized species. So we have two overarching study objectives. First, we want to examine the effects of the geolocators on the birds. In particular, we want to examine the physical effects of the geolocators. We also want to look at how are carrying the geolocators affecting return rates of birds, territory fidelity, and weight changes. And we did this by comparing a group of birds with geolocators and color bands to just a control group that just had color bands. Second objective was to examine the basic questions of where do they go? Where do our birds overwinter and what routes do they take to get there and back? And so for these, obviously, we can only examine these types of these types of questions with birds that have geolocators. We conducted the study at 2 sites. One is the Albany Pine Bush Preserve, and the other is Montague Plains Wildlife Management Area. And this is just north of Springfield, Massachusetts. Both of these areas support inland pitch pine scrub oak barrens, which again is an important habitat for the prairie warbler. The study was conducted in 2016 and 2017. I'll start in 2016 with the design of the geolocators and the harnesses we used to attach them to the birds. The geolocators we used were from a company called BioTrack, which is based out of the UK. Their dimensions were 19.5 by 6 by 3 millimeters, and they're collecting average light intensity at 2-minute intervals. The battery life was expected to be about 1 year. You'll notice there's no stock on these, and there's also no tubes or loops or any other thing for attaching the harnesses. In the absence of the stocks or the absence of these attachment locations, those were all, the absence of those things were all intended to keep the weight of the geolocator as light as possible, which was just under half a gram, just under 0.5 grams. To further decrease the weight, we also clipped back these metal nodes here. This is where we attach it to get the data. We clip those back a little bit to also reduce the weight. As for the harness, we used black Stretch Magic jewelry cord. So this is jewelry cord that's just used that kids will use or crafters will use to make bracelets and jewelry. We used we tied this jewelry cord into a figure-8 design with 14.5 millimeter loops. And then I used a drop of super glue to attach the harness to the underside of the geolocator, and then I cut off the extra length of the cord and then glued that onto the top of the geolocator so there were no loose ends sticking up. And this is what the final product looked like. And then finally, when we're heading out to the field, we would activate the geolocator the night before we expected to use it. That means we took it out of sleep mode and we initialized the clock to the current time. In 2016, we systematically worked across the study sites to locate singing males. When we found one, we would set up a net in a suitable location near the bird. So here you can see this is these are the poles supporting the mist net. We would set that net up in a suitable location, and then we'd lure the bird into the net using audio playback of another singing male and a decoy. And at the Pine Bush, we did that work between the 2nd of June and July 1st, 2016. At Montague, Mike and his team did it between the 29th of April and the 20th of June. And these dates were well within the breeding season when we could be sure that males would be aggressively defending territories. So here's me extracting a prairie warbler from the net. When we captured the bird, we marked them with an aluminum USGS band and a unique combination of 3 color bands. We determined the age and sex of the birds. We were targeting males, but sometimes females would fly in, so we always had to make sure that we had a male. We measured mass and wing chord, and then we also took a GPS location of the capture site. We put geolocators on birds that were over 8 grams. This was following the recommendation of the USGS bird banding lab, who wanted to ensure that the geolocators was as small of a percentage of the bird's body weight as possible. So for an 8-gram bird, the geolocators were a little more than 6% of the bird's body weight. And we attached the geolocator by slipping one loop over a leg, and then we'd position the geolocator on the back of the bird, on the center of the bird's back, ensuring that the light sensor was facing up, and then we slipped the other leg through the other loop. And then next we would work the loops up to the base of the leg so that the geolocator sat snugly on the back of the birds. And then finally, you can see here we tucked the feathers under the geolocator using a plastic rigid strip. We wanted to make sure that the light sensor was exposed. And so when we finished, we had something like this. In 2017, we needed to figure out who came back, and we had to recapture them. Birds tend to return to their territories from the previous year, so we looked for birds using the capture locations from 2016 for guidance. So these were the capture locations of the birds. Here's the Discovery Center up here. So this is out in Carner Barrens East. These were the locations of 2016. These were used as guides for where to go about looking for the birds in 2017. If we found a bird, we confirmed its identity based on, if we heard a singing bird, we'd look at it, try to identify the bird based on its color band. And we'd also search other areas for the birds for they may have moved. So again, we use this as our initial guideline, but if the bird wasn't where it was last year, we would search a broader area to see if the bird may have moved from where it was the previous year. If we found one of our birds from the previous year, we attempted to recapture using mist nets with audio playbacks again with the decoy. Most of our work was done between May 1st and May 23rd in 2017, but we did still pick up a few stragglers during our other bird work in the preserve as late as June 25th. And Mike had a similar situation. Most of his work was done between the 30th of April and the 31st of May, but he also had a few stragglers later in the season as well. And then when we recaptured the bird, obviously we recorded his ID, we remeasured mass, tail length, and wing chord. If they were carrying the precious cargo, we made sure we got that back. And then when we came out of the field, we hooked up the geolocator to the computer and downloaded the data. Okay, this is to show you how many birds we started with at the Pine Bush. We had captured and marked a total of 55 birds. 25 of these birds were given geolocators, and 30 were given just color bands. And most of these birds you can see were older birds or after second year birds, but a few were second year birds. And if you're not familiar with bird ages, the ages are based on calendar years. So if a bird hatches in 2015, as of January 1st, 2016, it's considered a second year bird. That bird may not be even a year old, but it's living in its second calendar year. And so by extension, an ASY bird, a bird that's an ASY bird in 2016, that bird would have hatched in 2014 or earlier. And then at Montague, Mike and his group had a total of 47 birds in their sample. 22 of those were given a geolocator and 25 of those just had color bands. You will also notice here, if you look at how many second year versus after second year birds he had, there they made a more concerted effort to get second year birds. As you can see, is by his much higher percentage of second year birds than compared to ours. Okay, so what happened to all these birds that were in our study? Well, in the Pine Bush, we started with 25 birds with geolocators. In 2017, 12 of them returned, and 13 of them either did not return or we could not relocate them. Of those 12 birds that returned, 11 of them were still carrying their geolocator. One of them was able to give it the slip. Because we do not know when this bird dropped its geolocator, I excluded it from the analysis. Of the 11 birds that came back with a geolocator, we were able to lure 10 of them into the net. We tried and tried and tried to capture this one bird, but we just could not get this sucker to go back in the net. We could not trick him into the net. And then of these 10 geolocators, I could get data off of 8 of them. 2 of them I could not, so I sent them back to the manufacturer and they tried to get the data off of them, and they told me that they actually had failed after a couple weeks. So, so out of the 10 that we got data off. As we handled it, we made sure it could bend its legs and that it could grasp with its foot before we released it. After we released it, we would watch them to make sure that they flew away. And if they can perch, all the birds were able to fly away with a geolocator on. And the ones that we were able to follow all the way until they perched, all the birds were able to successfully perch. But we couldn't follow all birds because if you're familiar with the pine bush, you know that it's scrubby and the birds can very quickly disappear into the vegetation. But for all the ones that all the birds flew and all the ones that we could see, fly and land, all landed and were able to perch. We indirectly noticed that some of their behaviors may have been disrupted. We caught a bird here. You can see this is a bird that we caught a couple weeks after we put the geolocator on, and you can see its node here is bent. That suggests the bird's either has been yanking on it or it got caught in vegetation. Neither one of those is particularly a good thing. We also had a bird come back the following year, and a bunch of the black weatherproof coating was ripped off. And the bird must have been after it for a while, and that's not really great because it means that they were messing with the geolocators instead of doing their bird thing. But these types of effects only happened in one or two cases out of all the birds that we monitored. As for long-term effects, the geolocators, the birds came back with their geolocators still above their feathers in nearly all cases. That was good. My worry was that the birds would preen around it and cover the light sensor with their feathers, but they did not. For the most part, the geolocators were remaining above the feathers. That did lead to some feather wear, as you can see here. This is after we took the geolocator off. And this isn't too concerning because feathers are replaced every year, so these feathers will be replaced and they'll be fine. And we did notice on many of the birds that there was a slight abrasion or callous skin underneath where the geolocator was. And this is probably because this is where the knot was used. This is where there's a drop of super glue that we used to attach the knot to the geolocator, and that may have rubbed a little bit on the bird's back. Okay, now if we look at return rate is a proportion of individuals that returned from the previous year. Now keep in mind that this is not equivalent to survival because it's possible that birds survived, but they just went elsewhere. They didn't come back to the preserve. We're obviously interested in the effects of geolocators on return rates. We expected birds with with geolocators to have lower return rates. We also examined wing length, age, and sight. We predicted that birds with longer wings would have higher return rates, and older birds would also have higher return rates. We included sight just to see if there was a difference between here and the site in Montague in return rates. So here are the results. There's a lot going on here, so let me walk you through it. For now, let's just focus on this upper left-hand panel. This is for second-year birds at the Albany Pine Bush Preserve. So the y-axis here is the proportion of birds that returned or return rate. The x-axis here is the wing length measured to the nearest half meter. The dots represent the number of, in this case, second-year birds that returned. Up here, that either have one, or birds that did not return, which are down here and have a value of 0. The larger dots indicate that the more birds that were occurring at that particular wing length. And the lines show here that return rates tend to increase with a higher wing lengths. So there's an increasing trend here with wing lengths. And you can also see that the lines show that the return rates for birds with geolocators, the dotted green line here, they were about 0.8 lower than birds without geolocators. And the shaded areas just represent our confidence in the trend lines. So now if we compare that to these other panels, you can see the same effect for wing length and geolocators exists for all the other ages and sites. But if we compare, say, the second-year birds of the pine bush to the second-year birds of Montague, we can see that the trend lines at Montague are almost 0.15 lower than they were at the Albany Pine Bush. And that's regardless of whether or not they had the geolocator on. The return rates were lower at Montague. And if we compare across ages, so if we compare the upper panels to the lower panels, you can see that the lines between SY and ASY, in terms of where they intercept here, the y-axis and where they go, you can see that those values are almost identical, indicating that age of the bird had very little effect on return rate. So out of all of these effects, the presence of the geolocators was the only one that was statistically significant. But the results certainly suggest that there was an effect of sight and wing length. And I say statistically significant if you're not familiar with that concept. This is just a jargony term for it meets the burden of proof. Without giving a statistics lesson on sampling error, statistical significance means that the difference we see basically are large enough to be real, and it's outside the realm of what can be obtained just by random variation in our sample. Okay, so now let's turn to our effects on territory fidelity. Territory fidelity is the tendency for birds to return to the same site in subsequent years. And territory fidelity confers advantages to a bird. If you're returning to the same site, if you're familiar with a food resource and you're familiar with the nesting sites and you're familiar with your singing perches, that's going to give you advantages over if you're in a novel location. So anything that causes the birds to have to be less site faithful, or is going to be able to anything that's going to cause them to be unable to defend their territory from the previous year, that could lead to lower survival and lower reproductive success. At the Pine Bush, we used capture locations as proxy for territory locations. Remember, I said we GPS the locations in 2016 and 2017 where we captured the birds. So we used those capture locations as a proxy for territory locations. At Montague, there they recorded multiple locations of birds each year. So for Montague, we use the average of the multiple locations as a proxy for territory locations. And then we use the distance between these territory locations as a measure of territory fidelity. So the closer the territories were, here you can see some of these birds were very close to where they were the year before. That's more likely if the territories were in the same location. Some of these birds that moved very far, those were birds that were much more likely to have moved their territories. And we examined the effects of geolocators on territory fidelity. Obviously, we're interested in the effects of geolocators. And we expected if geolocators were having an effect that they would be negative, that they would lead to lower territory fidelity. Maybe the geolocator would cause them to arrive late and their territory was already taken, or maybe the geolocator made it harder for them to defend their territories against rival males. So those were possible reasons why the geolocator effects would be negative. We also examined the effects of site to see if there's any differences between here and at Montague. So this graph shows the distribution of distances for birds with and without geolocators. The distribution of, so the distribution of distances for each bird with and without geolocators at the Pine Bush and at Montague. So the distance moved is here on the x-axis, and on the y-axis, this is the percentile of the distribution. And so you interpret the percentile like you would the birth weight of newborn babies. Right? So for example, if a newborn is in the 90th percentile, that means he or she weighs as much as the more than 90%, as much or more than 90% of the other newborns. The same interpretation applies here. So in case of the geolocators, I want to draw your attention to two things. First is that the curve without the geolocators, so the blue curve, notice it increases faster than the curve with geolocators. Second, notice that the curves at Montague increase faster than those of the Pine Bush. So to make this more concrete here, let's look at the proportion of birds that moved less than 100 meters at the Pine Bush that moved 100 meters, less than 100 meters between years at the Pine Bush. So 100 meters is a distance that's probably consistent with birds returning to the same territories. We can see that birds without geolocators, an estimated 43% of birds without geolocators were within 100 meters of where their territory was the previous year, compared to only 29% of the birds without geolocators. Now I'll compare that to Montague, and you can see there, 60% of the birds without geolocators returned within 100 meters compared to 45% of birds with geolocators. And then you can look at that at 200 meters or any other distances. You can look to see how those percentiles compare. So these results suggest that geolocators are having a negative effect on territory fidelity, and that birds demonstrated less territory fidelity at the Pine Bush. However, again, neither one of these effects for either geolocators or sites were considered large enough to be considered statistically significant. Okay, then the last effect of geolocator we looked at was the weight change. And so here we measured just as a difference in weights between 2016 and 2017. As before, we examined the effects of geolocator and site on weight changes. And what we expected was that if the geolocators were having an effect on weight, that they would be negative, that they're going to lead to lower weights. Perhaps because the geolocator is either impeding birds from obtaining as much food as their counterparts, or perhaps having to carry the geolocators led to an increase in energy requirements that birds could not meet. If they can't meet the energy requirements, they're probably going to lose weight. Our sample sizes were really small, and neither of these effects were statistically significant, so I probably should not make too much hay from them. However, I do find it interesting that the results ran contrary to what we thought. At the Pine Bush, birds with geolocators on average not only gained weight, but they actually gained more weight than birds without geolocators. And at Montague, all the birds on average lost weight, but again, birds with geolocators lost less weight than birds without geolocators. And again, I don't want to make too much about this, but if a weight gain actually happened, I don't in terms of speculating why this happened, maybe it's because the body weight composition of the birds carrying geolocator was different than those without geolocators. Maybe we unintentionally beefed up the prairie warblers. Maybe the weight gains in the birds with geolocators might have been primarily due to an increase in muscle mass because they had to carry this extra weight. And that's opposed to the other birds had an increase in mass, but that may be because of just increase in stored body fat. And muscles weigh more than fat, and that could maybe explain the difference why we saw a greater weight gain in geolocators. Again, this is sort of rapid speculation on my part, but I did find it interesting that the results ran contrary from what we thought. But again, this is based on not a lot of data. Okay, so now let's turn to our second objective, and this is where do the birds go? So let's start by looking at what does the data look like that these geolocators collect. So the geolocators were employed an average of 325 days at the Pine Bush and 343 days at Montague. And these things are recording light levels at every 2 minutes. So that equals about 250,000 light level readings per geolocator, about 250,000 light levels per geolocator. And this is what the raw data look like. So here's the data from, just from 2,000 light level readings. So this is about 3 days worth of data. So you can see here that these are the points here, and like up here, these are all points that are connected by a line. So these are these are here 2,000 observations, and this gives a kind of the ideal pattern. That shows a steep increase in light levels that to maximum. They steeply increase at sunrise to maximum levels. The lightest levels are sustained throughout the day. And then at sunset, the levels quickly drop off, and then the light levels are sustained at minimum light levels at night. And so here we have pretty clear twilight times, sunrise and sunset times, which is what's needed to determine latitude and longitude. Sometimes we have something less ideal that looks like this. What's going on here? So we have lots of downward spikes during the day. That could be due to shading from vegetation, or it's possible that the wings occasionally cover the sensor. And these shading events become particularly troublesome around times of sunrise and sunset. They can make it very difficult to know exactly when sunrise and sunset has occurred. And in extreme cases, if a bird is using a nest box or a cavity during the day, it would seem like the sun is setting and rising every time they enter and exit a cavity. That can make it very difficult to determine which is real sunset and sunrise times. Fortunately, prairie warblers are not cavity nesters, so they do not present that challenge for us. And the opposite can also be a problem. Imagine if a bird is nesting near an artificial light source. There would be upward spikes during the night, which could also make it very hard to determine sunrise and sunset times. We really didn't have any upward spikes at night, which indicates that prairie warblers are nesting far enough away from artificial light sources. Not to get too bogged down in the details here, but the data were processed with GeoLight. This is just a package for analyzing light level data written for a statistical programming language called R. There were 3 steps involved. One is the determination of twilight times, in other words, establishing sunrise and sunset times. Next, we need to calibrate sunrise and sunset times to a reference sun elevation angle. And then once we have times of sunrise and sunset and sun angles, we can calculate the positions of the animal. So I'll go through this one step at a time. Let's start with the determination of twilight times. So the most frequently used way to determine times of sunrise and sunset is called the threshold method. In this method, sunrise and sunset times are identified as the time points when light intensity passes a specific threshold. So here we say if it goes up above 2.5 units, basically goes up and stays above 2.5 units, that's considered, so here, this dashed blue line is the threshold. These dashed yellow lines indicate times of sunrise and sunset based on when the light levels exceed those thresholds or fall below those thresholds. Now, this threshold-based positioning requires calibration, which can be achieved by finding a reference sun angle to fit the recorded day lengths to the expected day lengths at a particular latitude at a particular site. Or sorry, at a particular date. And the differences in recorded and expected day length can be caused by shading due to vegetation, weather, or individual differences in devices. For example, in a forested habitat, recorded day length may actually be less than true day length. So a more positive sun angle is needed to provide the correct latitude. In other words, sun will have to be a little bit higher on the horizon before you get, before it appears that the sunrise has occurred in the forest. So to calibrate our devices, we examine the sun elevation angles from the first 3 weeks after the geolocator was put on the bird. So this is the first 3 weeks they were when they were first deployed at a known location. So these birds were on territory, so we knew where they were and what the sunrise and sunset time should be. This shows the variation in the sun elevation angle for this period and the resulting error in twilight times in minutes. During this time, the actual sunrise changed by about 10 minutes and sunset times changed by about 2 minutes. And these changes in twilight times resulted in changes in latitude, which I'll come back and show you what that looks like in just a second. But to get at what is our sun elevation angle, what we did is we used the median sun elevation angle to represent the sun angle in subsequent calculations for positions. So using this sun elevation for the entire year means that the shading, weather, and behavior during the calibration period, we're assuming that those are going to be similar throughout the entire time the geolocator is on the bird. Okay, now once we have sunrise and sunset times and sun elevation angle, we can calculate latitude and longitude here. We can calculate latitude and longitude, and here's just a figure showing you how this works conceptually. So here's a picture of the Earth flattened during the Northern Hemisphere's winter. This shows what part of the globe is being illuminated at a specific time. So the light dark boundary here on the left shows sunrise, and the one on the right shows sunset. Where they meet in the middle here, this is solar noon. So if you follow this point in the US at sunrise, the Earth rotates towards the east until the sunset occurs, which is this boundary. And the width of the illumination, the width of this illumination period, that represents day length. And you can see how day length changes with latitude. There's 24 hours of darkness of sunlight in the Antarctic. And solar noon occurs, 12 hours at the equator, and then 24 hours of sunlight. Sorry, did I say that right? There's 24 hours of darkness in the Arctic, 12 hours at the equator, and 24 hours of sunlight in the Antarctic. And solar noon here just occurs at the median, is at the meridian at which the sun reaches its northernmost point on the globe. So day length gives you latitude, solar noon gives you longitude, and there are standard astronomical equations used for converting subsequent twilight events and sun elevation angles to latitude and longitude. So here's an example of a graph that's derived from sunrise equations that gives you day length. So suppose we're at about Julian day right now, about 1:20. If we know we have a day length of about 14 hours, what is its latitude? Its latitude is about 40-something degrees north latitude, and that's our latitude here in Albany, right? We have about a 14-hour day length. We're somewhere around Julian date 1:20. But what happens on the equinox? So on March 20th here and on September 22nd here. So Julian days 79 and Julian days 265. What information do you get about latitude during the equinox? So here, if you go to these days and look at the line of daylight, you can see here at 12 hours, it could be any possible latitude. On the equinox, on the spring and fall equinox, we have no information about latitude because day lengths are 12 hours everywhere. And so we'll come back with how to deal with that. Okay, now before I get into the results, I just wanted to lower your expectations a little bit. So this map contains the positions of a single bird during the 3 weeks after the geolocator was deployed. This bird was on his territory in the Albany Pine Bush, so ideally all of these locations would be hidden under the X on the map. Yeah, I know it's, we knew we were going into this that it wasn't going to be very precise, but not being familiar with the technology, we were hoping it was going to be a little better than this. We can look at this in a more quantitative fashion. If we measure how far away each of these estimated locations are from where the known location here at the X, we can look at the difference in latitude and longitude. So if we plot this, the average location and the error bars for each bird, you can see that the error bars here represent basically the inner 95% of the distribution of distances. In terms of accuracy, the longitudinal error was greater than the latitudinal error while the bird was on site. And the precision, in terms of precision, the latitudinal data was much more variable than the longitudinal data at the Albany Pine Bush. And at Montague, the variation in latitude and longitude were sort of nearly equal, one way or the other. So the precision was not great on the breeding grounds, and it didn't really improve during migration. Here's an example. I'll just show you the locations of a bird over time. So just pay attention to the variations in latitude. So the bird was captured up here on July 2016. Here are the locations for just about for the month after it was captured. So as we head towards the equinox on September 22nd, you can see that the latitude here starts to get very imprecise. And during the equinox, the latitudes are highly variable. Here's the equinox. You can see the latitudes are very highly variable, but you do notice that the positions, location shift west. They start to shift back east on the other side of the equinox, but it's still highly variable. And then things settle down a bit from November to February, where they're overwintering. And as we start to head towards the spring equinox, latitude becomes unhelpful again. You can see the latitude of these points are all over the place. And then as we moved into April, you can see the birds would move west, then they move up the coast, and then this bird was recaptured back in the pine bush on the 23rd of May. So here's another way to look at these data. So if we just look at how the latitude is changing over time, here the solid black line represents the latitude of the pine bush. And the gray area here represents the latitudinal band of Florida, and the green band is a latitudinal band containing Haiti and the Dominican Republic. So the latitude is very noisy around the equinox. Here, you can see it goes anywhere, it goes almost from the way far south to way far north on the globe. And unfortunately, fall migration happens during the equinox. So fall migration is hard to pick up using geolocators because it happens during the equinox. But even outside of the equinox, you can see how noisy the data still can be. For example, in here you can see that based on the latitude, this bird can be anywhere between New York and Florida. And this is July to August. This bird was probably in New York still, or still close to New York, but you can see the variation here. And you can see that that variation is very noisy throughout. So latitude is not super helpful. Fortunately, longitude is less sensitive to the equinox, and it provides a somewhat clearer picture. So these shaded areas represent the longitudinal bands associated with Florida, Haiti, and the Dominican Republic. The solid black vertical line is the longitude of the pine bush. So time advances here from top to from bottom to top. Sorry, so we'll start down here in July 2016. You can see that we're in the longitudinal band consistent with the pine bush. And then starting around October, you can see the longitude shifts east into the longitudinal band that's consistent with Florida. Then there's a shift east that corresponds with this movement from Florida, probably across Cuba, and then into Haiti, and then into the longitudinal band that's consistent with the Dominican Republic. It stayed there through the spring equinox, and then, which is here, this dashed line, it stayed through the spring equinox. And then in the spring, it made its return trip, probably again back across Cuba to Florida, and then moved west. And then it moved back east as it moved back up the coast to New York. So all birds generally showed this east-west movement in the fall, and then west-east movements in the spring. The difference was primarily in the longitudinal band in which they overwintered. Some overwintered in the Dominican Republic. Here it's birds from the pine bush in Montague. They're in the longitudinal band of the Dominican Republic. Here you can see these birds were very consistently in Haiti. And then you had some that were a little more messier that might have been close to the border of Haiti and Dominican Republic. It's hard to say one way or the other exactly which side they were in. So it was hard to make a call just based on the longitudinal data alone. So if we look across all our individuals, it looks like they're all taking this general pathway north and south. Overwintering grounds is a bit tricky because we have to account for the longitude and the latitude. So here's a cloud of points. This covers a pretty big area. So you could guess where the points tend to concentrate, but that's going to be pretty subjective. And I've been messing around with the kernel density estimator to quantitatively characterize the activity centers. So basically come up with a more objective way to say, where are these birds concentrating their use? And so now you can see, once we put this on, you can see in all likelihood, these birds are probably, this bird is concentrating its winter habitat use in Haiti. And I did this with all individuals. So here you can see, and from the pine bush, we had 3 of our birds were in Haiti. Montague had 3 of their birds in Haiti. So a total of 6 of those 16 birds that we had data on were in Haiti. 4 of them occurred in the Dominican Republic from the pine bush. 2 of the birds from Montague wound up in the Dominican Republic. And then these guys were, we had 2 birds from the pine bush that were in the Turks and Caicos Islands. We're up here, which are north of Hispaniola, north of Haiti and Dominican Republic. We had 2 of our birds from there and 3 from the Montague Plains were in there. So this gives you the distribution of the birds across those wintering areas. So I wouldn't put much stock in these specific numbers because sometimes it's hard if they're on the border of Haiti and Dominican Republic to make one call or the other exactly where they're at. But the big thing here to take away, I think, is that from each of these breeding locations, each of the birds from each of these breeding locations, from the pine bush and Montague, both ended up in the same wintering locations. So that there didn't really appear to be any sorting of the breeding populations from either Montague or pine bush. They were both going to the same overwintering locations, and they were very likely mixing on the overwintering grounds. All right, so then to wrap up, thank you for sticking with me. Just to make some conclusions here. The light level geolocation appears to be a viable method for studying the migration of prairie warblers and very likely other small songbirds. And really currently it's the only method for studying birds this small. It clearly has some limitations. There may be some negative effects on some individuals, as we saw with return rates. But the potential for geolocators to have negative effects shouldn't necessarily just disqualify their use. Rather, the magnitude of the negative effects need to really be considered against the benefits of the information that's gained for the population of birds. And the low precision in the locations does make it hard to determine specific overwintering grounds and migratory stopover sites. And this is especially true for the fall migration because it happens during the fall equinox. And this isn't great, but let's not lose sight of what we're doing here. We're strapping a 0.5 gram light sensor on a bird that weighs a little over 3 pennies. The thing's flying to the tropics and back. And any information that we're getting, I think, off of these birds is still pretty impressive. But even with these limitations, I think we are still getting some useful information. For example, we know based on the location, especially based on the longitudinal data, it looks like birds are coming down the coast, down across Florida, across Cuba, and then back. So we know these birds are moving down the coast as opposed to some other bird species like the black-polled warbler, which actually launches off across the ocean and flies all the way to South America. So the birds are moving up and down the coast. We also have a general idea of where they're overwintering. And the main wintering sites for these species appears to be on the island of Hispaniola. And if this is the main wintering grounds for the prairie warblers, it is a cause for concern because the forests of Haiti and Dominican Republic are almost entirely gone. They're really being hit hard down there. So solving one mystery with respect to fall migration routes of the species has opened up even more pressing issues of conservation of critical habitat. By identifying non-breeding habitat usage, particularly at major migratory stopovers and non-breeding sites, it's now critically important now that we know where those sites are, that we look into those sites and ensure the conservation of those sites for this warbler. So then just to wrap up, I wanted to acknowledge the efforts of these fine people. These people helped me with all aspects of the field work, which required many long days and often weekends. They were really instrumental in helping get the data collected, and I was really lucky to have their help.